More I press that how to change that by not
Ladies and gentlemen, please welcome to the stage our industry chair, Melvin Greer, and our government chair, Justin Herman.
Good morning, everybody. Thank you so much for coming out here this morning, this early in the morning as well. Quick question, how many people in the room are here from industry? All right, how many people are here from government? All right, there's a great mix here. So thank you again. Here to the ACT-IACT Artificial Intelligence Forum.
Hello, I'm Melvin Greer. I'm the Chief Data Scientist for Intel Corporation Public Sector, and I really want to join Justin in thanking and welcoming all of you, and especially thanking the volunteers for this ACT-IACT event.
Awesome. We keep going back and forth looking at the scripts here, so I'll look directly at you on this. So one of the things that we see, and just to introduce myself, I'm Justin Herman, and so I work for the Emerging Citizen Technology Program for GSA, which covers government-wide support and coordination for new technologies that we know that federal agencies have use cases for, are interested in investing in, but no clear roadmaps exist to go forward on. So right now our main focuses are artificial intelligence for citizen services and blockchain, but we also cover virtual and augmented realities and social and collaborative technologies. And one of the things I was wanted to mention this morning, we were trying to save it for our honeymoon, but we read, that's supposed to be a joke. Okay. Is one of the ways that we're trying to approach this is that one of the things is, and why I was so interested when ACT-IACT came and said we really want to do this artificial intelligence forum, is so many people do not know what actually is going on in artificial intelligence for the federal government. And then when people do talk about it, it's either articles talking about, you know, the Terminator or some dystopian future, or there's conversations about visioneering about what things are going to look like in 5 or 10 years. And what's getting lost in the equation is the practical day-to-day things that are happening right now, where people might not even know that they're using artificial intelligence. They just know that their programs and services went better. And so that's one of the reasons that we were so attracted to not only ACT-IACT's vision for what this event could be, but what we could do together and how we could make this a more engaging program, because if we're not talking about those practical things and showing the full scope of use cases, diverse approaches, and diverse applications across the federal mission space, we are doing a grave disservice to the federal community. But that stops now. And it's because you're here this morning and this dedication that this is a challenge that we're going to be overcoming. Now, in particular, and I mentioned something that we were saving, but it's already in the press this morning before it was ready, is we've released now, or it was released for us, it's called the Emerging Citizen Technology Atlas. Essentially, so when day-to-day, when we're working with federal agencies, working with businesses, we are sitting on repositories submitted directly by agencies on hundreds of use cases, and not just how they're using things like AI for citizen services today, but how they want to do it tomorrow, what they're looking at for investment. These are all repositories that we have had, and now we've open sourced the whole damn thing. So you can see what we see, you can understand what we understand, and we can start creating the narrative of the full scope of what AI for citizen services is for the federal government. There's actually entire blank pages on it right now because I said we're still building it. We were going to get it done at the end of this week, but you're going to start seeing that in the press. And what we would ask ask you to do, the same as we have all government agencies doing right now, is you can go through GitHub and you can start loading up resources in AI. You can start loading up use cases, and you can start linking to the programs that you know about and that people need to know about. So thank you so much.
Yes, I agree with Justin. Intel too is very, very excited that you're here. As the industry chair, I can tell you that we have seen a tremendous amount of excitement and very much a lot of growth and interest in artificial intelligence in government. And that's one of the reasons why Intel has invested more than $1 billion in creating government solutions that can be used immediately. If you go to intel.com/AI, you'll be able to see many of the very important acquisitions that we've made in cognitive computing, machine learning, deep learning, and convolutional neural networks that can operationalize your mission. So we're very excited that you're here. And before we get started, I want to make sure and thank our two sponsors, ASRC Federal, who's the largest Alaska Native corporation. We're very happy that you're here and appreciate your sponsorship. And of course, our friends from IBM, who are also working very hard to operationalize government missions in artificial intelligence.
Awesome. And also, we would like to thank all the volunteers from both industry and government from ACT-IACT who helped put this together. And as Haley and Carol can testify, they probably needed AI to process all the emails going back and forth about this. They are saints, so please thank them on our behalf. And then I think we have just a couple of quick housekeeping notes as well.
Yes, and so I'm going to go ahead and read them so that there's clarity around them. First, remind you that this is a vendor-neutral event and that there is press in the room, so everything's on the record. Also, IAC will be sending out a short outline survey following the event, and we certainly want your participation and your feedback around how the event is going. And then lastly, we want to remind everyone that's tweeting or using social media that the hashtag is @ACT, IAC.
Awesome. Also, some housekeeping notes. This event is eligible for 4 CLPs. Please stop by the registration desk to fill out a short form or email training@actiact.org. Justin exits the stage I just read. So. I want to read that like Darth Vader.
I know, right. So in the interest of fair play, the Intel Chief Data Scientist has the pleasure of introducing our keynote, and that is Dr. May Casterline. Dr. Casterline is a data scientist, image scientist, and software developer. Her research interests include deep learning, hyperspectral and multispectral imaging, and innovative applications for machine learning and remote sensing, multimodal data fusion, and data workflow. She holds a PhD and Bachelor's of Science in Image Science from Rochester Institute of Technology with a focus on remote sensing. So we're very pleased to have Dr. May Casterline.
Thanks. Thank you. Okay, hopefully everybody can hear me. You guys good? Okay. Hello, so I'm May. I'm from NVIDIA. Thank you all for having me. I was pretty excited to see this event, actually. It kind of came together at the last moment for me personally, but I operate in the federal space for NVIDIA, so watching the federal space get more excited about AI, in my opinion, is long overdue. Industry is much further ahead, and so I'm excited that there's interest, and you guys are here and exploring how it can help you all. Should I just click this thing? Oh, this way? All right, so I'm here to talk about AI for government somewhat. Mostly AI. What is AI? What's it doing in industry? Like I said, I do operate in the federal space, so I spend a lot of time trying to help various organizations, whether it's federal integrators or agencies, integrate these types of technologies into their workflows. But there's a lot going on outside of government and can be translated into government. So first, NVIDIA. What is NVIDIA and why am I here? NVIDIA actually got started as a gaming company. Some people might know that, particularly if you have kids that do video games. We make graphics cards. And this started, 25, 30 years ago. And slowly we've sort of started to move into the virtual reality space, again, very graphics intensive process. But recently, in the last 10 years, we've moved really heavily into artificial intelligence, high performance computing, and then applications like self-driving cars. So the sort of common thread between all of these is it takes GPU computing power to sort of make all of these things happen. So what's really driving this are all of these massive achievements in AI, and you guys have probably seen all of this in the news. A lot of these make really flashy headlines. So the Play Go competition, a computer beat a human playing Go for the first time. It's I have no idea how to play that game, but I'm told it's very complex. Computers can now play video games. They can synthesize voices. You can train robots. We have a very fascinating project where we're training robots in virtual reality and then just downloading trained models to a physical robot and then releasing it to go do tasks in the world. So you don't actually have to physically train a robot. You can do this all in VR, so it's a nice mesh of the technologies. There's image to text translation, writing captions for videos or imagery, auto-labeling imagery. And autonomous driving is obviously a huge push into the future, and we'll just kind of keep growing. So this whole massive explosion in AI is really driving our investments and the way we're looking at our GPU platform in general. So sort of a startling sort of comparison, if you look between 2014 and 2017, that's the difference in numbers of companies that have engaged with us to sort of execute different AI techniques, incorporate our technology into their processes, learn about our software, things like that. And we spend a lot of time integrating with all of these things called deep learning frameworks. So deep learning frameworks are the software development kits, sort of the libraries that developers and data scientists use to build these systems. What they actually do, which makes this much easier, is they abstract sort of the heavy-duty GPU level processing that you need to do to make these things efficient into easy to sort of weave together APIs to build out software that executes deep learning. And so we work with all of these folks, sometimes weekly, to keep them in lockstep with our lower level software libraries and our hardware so that the optimizations bubble up to developers without them having to worry about the minutia of what changed in CUDA 9 versus 8 and things like that. And then along with all of the software work we do, we obviously produce hardware, and that hardware is seeping into all of the systems from desktop up to cloud service providers. So while all of this is going on, and there's obviously a really big push outside of government, NVIDIA does have a federal team. I'm on the federal team, and our whole mission is to advocate for AI in the federal space. It's not something we charge for or anything like that. Like, we're here just to find people that would like to do cool AI projects and help you go. What kind of hardware do you need? How do you use the software? Are there other people working with you or that you haven't met that you should be working with? Things like that. And so we have touch points and have been working in DOE for a long time, mostly because of high performance computing applications over there. Obviously defense, that's sort of the world I come from. My background's in remote sensing, so satellite imaging systems. Commerce in the civilian side, as well as NASA. So we're here making contacts in these areas, trying to figure out who's doing what and push the art of the possible into all of these spaces. So, like I said, a big part of what we make is hardware. I'm not going to talk too much about the hardware, but it is sort of everything from desktop to cloud, depending on your use case. But here's where I kind of think things that people don't tend to think about when they think about NVIDIA is, like, we have the hardware, and that's fantastic, but we spend a lot of time building out the software layer. We actually have more software engineers at our company than we do hardware engineers now because of this. And all of our software is free. You can just go download it. So the baseline underneath the software is the SDKs. This is the lower level libraries. And then again, on top of that, we work really hard with outside partners to integrate our lower level SDKs with the more application focused touch points where developers and users would start to really interact with the GPU and make things happen. And then all of these sort of well integrated stack approaches leads to applications. And so we work to highlight those and make them the best they can. We will help anybody who needs help getting going. All right, so we make all this cool stuff. We build all this software. Why are we doing this? Why are we spending so much time working to make all of these things work together? And that really is deep learning. Deep learning is what has ignited this whole revolution in computing models. I just wanted to go over it briefly. I know that there's developers in the room, so this might be sort of old hat, but maybe nobody knows what deep learning is, and everybody just keeps telling them the robots are going to do everything, and everybody's like, how? So this is kind of it in a nutshell, and I'll do it briefly. Before, when we were trying to get systems to do things, take in data, make some decision about the data, it involved what I would call a SME. A subject matter expert needed to be in the loop, deciding the math that the signal would go through to produce the answer. I want to be able to find all of the staplers in every image that I see. So they build a staple finder, right? They think this is the staple shape or stapler shape. It's kind of these colors. You build all these discrete building blocks that your signal flows through, and it can find a stapler. The problem with that approach is it does take a lot of time to do that. You have to know staplers really well. And you can obviously see this is a silly metaphor, but you could extend this to much more complicated problems. But the next day, somebody comes to you and is like, I don't want to find staplers anymore. I want to find turtles. That thing's not going to find turtles. You have to go back to the drawing board because it's an engineered solution. If you create an engineered solution, you get engineered results. You will only find staplers. So the interesting thing about deep learning is it pivots this sort of approach and becomes more of a, it's not more of it is, a data-driven technique. So deep learning consumes massive quantities of data and learns from the data the signal it needs to detect the thing you're interested in. You say, here's a pile of data. I want to be able to find these types of things. Please learn that. The way you do this is with training data. You guys might have heard of this, labeled training data. So this is a manually intensive problem still today. There's obviously research in what I would call unsupervised learning, which involves unlabeled data. But broadly, training data is going to be a requirement to get these things going. So these are labeled things. So that's a picture of a stapler with the word stapler next to it. And you're going to use that to train the system. And basically how these things work is it's a computationally intensive iterative method of computing the sort of transfer function that the program needs to convert pixels to the word stapler. And this is sort of a cartoon, but these are actually networks of mathematical functions. And we don't need to go into any more complexity than that, but the main point is they start off knowing nothing, and as you move the data through the network, it alters the way it reacts to the data such that it gets closer to the right answer in subsequent tries. And so you do this iteratively, and then at the end you produce what's called a trained model. A trained model is that network with the adjustments that you have sort of encoded into it via the training process. So at the underbelly of this, though, how do you actually mechanically do this? This problem boils down to a massive matrix mathematical computation problem. So we have this massive iterative computation that involves matrix math. Well, guess what? The GPU is perfect for that because that's exactly what graphics rendering is. And so that's why NVIDIA is able to pivot to AI without massive disruption to what is our fundamental platform. We have a processor that is built for this type of computation specifically. So this is sort of a eye chart of a graphic, but I think it sort of speaks to why a change in the compute model is going to be necessary. So what I just said is we need to do massive amounts of parallel computation. This problem is only growing. Networks get deeper and more complex with more complex problems and more data, more computation. I need more cores. So we come to Moore's law. Now Moore's law states, it's kind of like a rough estimation that every year you could double the amount of transistors you could fit on a chip, and you could double performance. And that worked really well for a really long time. So you see that blue line, single thread performance? That's kind of a measure of compute performance relative to the number of threads you could run on a CPU. So the problem becomes, though, the CPU is not a throughput designed device. It's a latency designed device. It's doing a lot of different things. It's managing mail, it's managing the operating system. The user has to do things and it doesn't want to wait, right? So it's perfect for that, and they're fantastic. But when you want to jam a bunch of math through it, it locks up everything else you want to do. And if you actually need to grow and scale, you need to be able to add more cores. The GPU is designed to do that. So the main advantages to deep learning is it's robust. I don't have to sit down and tell it what a stapler is. I can just give it a pile of data, and it can learn what the stapler is and what the signal is that denotes a stapler, and the other things. You don't have to plan in all of your edge cases to when it's going to fail. Maybe all of a sudden somebody took a staple picture from the top and it doesn't know that that's what a stapler is, right? So you can feed it a pile of data, it observes all of the different variations, and it learns that without you having to explicitly say, this could happen, be prepared. One of my favorite parts about deep learning is what I call the pivot. So you can train a model to find cats and dogs and things like that, and that's a lot of what the academic data sets are, right? They're based on a collection called ImageNet, which are kind of natural perspective, human observable images of cats and bicycles and all sorts of things. It's huge, well-labeled data set. But that's not everybody's problem. My problem in particular is I would like to find an airplane in one giant country, or maybe all the airplanes, right? I get that. People ask me that, or find my truck. I don't know how many times I've been asked to find a particular truck. So how do I, and then they caveat that with, I have no training data, which is a problem. However, these things are generalizable. I can take a trained model that was trained on cats and dogs and slightly alter it and train it with a little bit of labeled airplane data, and now it can find airplanes. So you can take models that were purpose-built for something, do a incremental amount of work, and now they're applicable to another domain. And they're scalable. You can just give it more data and it will learn more things. You don't have to really, I mean, there's obviously nuance to that, but the theory is there. So some use cases. I know there's a lot of folks that are going to talk about use cases in the government. Because of where I work, I can't tell you about a lot of the use cases that I'm working on, but I wanted to highlight some, and hopefully some of you folks will have some really cool projects, and I'd love to talk to people about them. So one sort of the highlight, NVIDIA's engineers and our compute resources are involved in the Cancer Moonshot program with DOE. So this is using AI to do all sorts of, I'm not a medical person, so I can't really speak to it that deeply, but they're doing some really cool work, and they're using a lot of our scalable hardware to tackle this problem. This is interesting, a radiology example through NIH. A big problem, obviously, like I mentioned, is training data. And so they use an AI technique to generate the annotated radiological data set to start training models to detect different diseases in radiological imagery. Next. This one's fascinating. This is Benevolent AI. So it's, again, a medical application, but a slight twist. So what they're doing is using what's called NLP, natural language processing, which is another big area of research for deep learning, to consume research papers and then be able to give researchers ideas based on all of the research as to what to pursue, what's most likely to work, what's being talked about in what way, and how is it being discussed, and what should you pursue, right? So if you've ever actually gone to like PubMed or ArcSiv or any of these things, it is impossible to keep up with research papers and figure out what everybody's doing. Most likely 10 people are doing the same work at any given time, anywhere on the planet. It's probably more than that. That's probably gross underestimation. However, they're using NLP to consume all of that content and make these sort of give researchers the keys to move forward without having to comb through everything. Cyber is a big area. Accenture is a cybersecurity lab that uses NVIDIA GPUs to consume network traffic. Network traffic can be expressed as a graph, which is nodes and edges, connections between places and data. And they're using that to detect alerts of sort of potential threats and things like that. This is actually a Chinese company that is contracted with their weather service to do cloud predictions from radar images. What types of clouds are these? And serve them up on apps and things like that. So broad application in industry all over the place. So this is a highlight of a NASA program called DeepSat. So remote sensing world kind of latched onto deep learning. It's been a little bit slow, but it's getting there, and all the major providers or commercial providers are jumping on board. DeepSat's interesting. They've produced labeled training data and their own kind of framework, particularly for working with remote sensing data. Because remote sensing data is not like cat pictures. There's a lot of problems that you wouldn't necessarily know to anticipate unless you've worked with the data before. So anyway, so this is a very interesting project, and it's open source, so you can go and grab this. So hopefully the key sort of takeaways here is that AI is sort of everywhere. It's coming, and it's a different way of thinking about how to compute data and extract information from what's coming in. And we're here to help that happen. And I'm happy to talk to anybody about their projects or if they want to get started, anything. And I will just do a little plug for our conference, which is November 1st and 2nd. It's GPU Technology Conference. If you're government, it's free to come. You just have to register. Industry, there is a fee, but I can actually get you a discount if you guys email me. But there's going to be a lot of great talks. It's a 2-day event here in downtown DC. I'm going to be running a training labs. There's a lot of training opportunities, hands-on labs and stuff like that. And so that'll be here November 1st and 2nd. So that was kind of my spiel for you guys. I don't know if we're supposed to take questions or if you guys find me later. I don't know what the deal is. Okay, we are doing questions.
Thank you. Good morning.
Hi.
I'd like to ask when it comes to developing conversational agents, really sophisticated conversational agents, what applications have been done to deep learning to improve them in terms of their knowledge of the domain and their ability to interact with humans?
You know about like chatbots?
Yes, sir. Yes, ma'am.
So I'm not familiar with chatbot technology personally. There actually has been a lot of hilarious chatbot things happen recently. So those types of modeling techniques are called reinforcement learning, and that is making that's an area that hasn't sort of weaved its way into remote sensing yet, but I think it has an application. Anything with sort of a temporal sequenced approach will benefit from reinforcement learning, I think, right? Because temporal means something could come in and change what's going to happen next, and you sort of need the sequence to help predict.
Right.
So I don't have anything specific to tell you, but I could probably reach back, and we have a whole research group that does that stuff.
Second question, if you don't mind. You represent a hardware company, so I have a hardware question. A major component of the Chinese movement to AI is developing these huge monolithic chips. These things are the size of a graham cracker. They don't care about scrap rates because they don't care about cost. Mm-hmm. And do you see any, aside from the cost limitations, do you see any other technical limitations about that technical approach of just making the chips bigger instead of faster?
So I'll answer it slightly differently, and it might not be the right answer. But again, I'm not a hardware person either, but the way I would answer it is there's a lot of people trying to make different types of chips, purpose-driven chips that do one thing. And I would say that any purpose-developed chip to do one task will beat a GPU, most likely, in that scenario, because it's designed to do that. Somebody poured engineering resources into making that chip do this one thing the best. The argument I would say against that is it's the same engineered solution for an engineered problem. You're back to the stapler detector, right? That chip can't find turtles because it was trained to find staplers. So large chip manufacturers that are going, that are building, FPGAs or ASICs, right? So they're going to run into that. They're going to come up with very tuned solutions. But on top of that, not only do they have to do that once, they don't have a platform to build on top of, right? So like CUDA is an investment that we made 10 years ago, which is our underlying software development kit. And CUDA is broadly applicable. We keep adding new applications, and we have a developer base that's huge. So you can actually go find somebody to work for you to program a GPU. Those types of chips, they're going to be delayed in being useful because they have to build an entire firmware and software set that works with them. And so that means they got to go find a developer who's got to dream up this thing, and then they have to tell a bunch of other people about it and get them to latch onto it. So that's kind of how I would answer that. I don't know if that's exactly what you, that was it? Okay. All right. I think they want to give you a microphone. She's at the center table. Oh, sorry, I'm sorry. Maybe there's more than that.
Thank you for sharing your expertise. I have a quick question about where does human-in-the-loop AI fit in?
Yeah. So, there's a lot of excitement, and then there's fear about AI too, right? Everybody dreams up the worst sci-fi scenario about fear, and humans are going to be pushed out of this process. I will say I don't believe the technology is there yet. It can do beautiful, wonderful things, but we still need humans in the loop, primarily for feedback, as well as the decision making. The technology is not ready to make decisions. It can make suggestions, but we still need common sense humanity in the loop to absorb those suggestions and decide what to do with them. Just the loss functions in the training scenarios are not sophisticated enough to create an entirely sentient being in my mind. So humans are integral for the feedback process. So when I say feedback, I mean I produce a bunch of suggestions. That there probably some of them are right and some of them are wrong. Tagging those is helpful, right? And that's the feedback part. The human says, nope, that's not right. Yes, this is right. And that information goes back into the training cycle. The model gets better, the suggestions get better, and the time to decision that the person makes gets shorter. And so and not only that, just the modeling aspect of it, while these things are really smart, they can go off the rails pretty quickly. So it's not like there's a formula to follow either. So human, developers are required currently to make models produce the answers that you do want. It's just not as engineered as it was before. Any more?
Hello.
Oh, hi.
Hi, how are you?
I'm fine.
So what you've talked about when he was talking about his chip over there, I don't know what it was, but I do know that both Google is talking about something called a TensorFlow, and I think Amazon is coming up with something, and they're all coming up with their own chips. How do you think that's going to play out versus a more, simpler, if you would, GPU kind of processor? Yeah,
so the TPU, the Tensor
TPU,
Processing Unit. Yeah, so another purpose-built chip. So we work with...
Purpose-built for AI.
Yep, okay. Purpose-built for AI. So we work with Google pretty extensively, actually, and they're a huge consumer of our GPUs, which says something, right? They don't have an army of TPUs, but they're great. They are really pushing the bounds on research. They create great software. So I would go back to the same argument. The TPU will exist, and it will be great at matrix math. It exists. I mean, I don't think anybody can use it yet except for Google people, but it's there. But again, you have to grow a developer base, and in order to grow the developer base, you need to be able to interact at a firmware level and sort of abstract that away. And so I would just say they will probably get there, but we're ahead. Good? Okay, I'm getting the hook. So, thank you all very much.
Go do another
All right, thank you so much for that. And I would like to welcome back to the stage the industry chair for this event, Melvin. Thank you so much.
Thank you very much. I'd like to invite the panelists for the government panel to come up. As I mentioned this morning, Intel's invested $1 billion in artificial intelligence. It's the largest corporate VC in the acquisition of artificial intelligence and data science capabilities. What you might not know is that 60% of those acquisitions are in software. And the reason why they're in software is because our strategy leads with this concept of software. And this is where we're seeing a significant amount of discussion in the federal government, because they don't make chips in the federal government, but they do build software. And software is what's really driving the artificial intelligence revolution. So I'd like to welcome a government panel that we helped organize and discuss some of the things that I think might be important for you to think about. I'll introduce the panel very briefly. We have Jeff Alstott from IARPA. Anybody not know what IARPA stands for? It's the Intelligence Advanced Research Project Activity. And then we have another Jeff Butler from the IRS. And then we have A. Michelle White from the GSA. We were going to have Ariel Gold, but unfortunately, as you probably can imagine, sometimes you just get called into a government meeting and can't get out of, and so Ariel has been unfortunately unable to join us. But we're really happy that you guys are here. And so Jeff Butler, I want to start off with you right off the bat. We know that there are lots of different kinds of artificial intelligence and or this thing called data science. I'd like for you to give us a sense of what kinds you see out there and what kinds are the IRS actually adopting.
Thanks, Mel. First, it's a pleasure to be here and talk on behalf of the IRS. The first thing I want to do is just step back and talk about the seemingly endless frontier as we know it in our research community, which I'm a member of problem-solving opportunities. The sheer scale of opportunities at the IRS alone, because of the size of our business environment, is frankly stupefying, and it keeps getting bigger thanks to data and advances in technology. So just a couple of high-level data points to motivate that picture. Last year, fiscal year that we concluded in 2016, $3.3 trillion collected. 3 billion information documents received. These are the 1098s, 1099s, all of that you're familiar with. Nearly $500 billion of refunds dispersed through financial settlements. Phone calls, north of 75 million. Web visits, over 500 billion. These numbers are not found anywhere else, at least in the United States that I know of, if even on the planet when it comes to tax administration. So just to think about the opportunity space there are a lot of challenges, but a significant number of opportunities for improving business functions, business processes, many of which are legacy in nature, some of which are frankly outdated and need radical overhaul. And then service delivery to the taxpayer really is what the IRS is most interested in as one of our statutory mandates. And in doing so, we really want to improve, like other agencies, improve benefits to society along the way. So with that backdrop, Mel asked a specific question. I'm going to break down into two parts and keep my answer under 3 hours as I committed to. First part is, what is the IRS doing today in terms of data science and AI? And I'm going to use that interface because Mel, you use data science, and I think there's a strong connection here that needs to be made. First, we're using a lot of traditional methods that I think are going to be talked about. May talked about areas of machine learning, natural language processing. These are great subfields of AI. They've been around for a long time. Not artificial general intelligence. We're not talking about the scary super robots, the gun-toting robots that you see with the scaremongers that are out there that May alluded to. But we're cutting across most of the practical subfields of AI: machine learning, natural language processing, image processing, speech recognition, knowledge representation, and evolutionary programming. Those are the key areas. In machine learning, we're interested in the usual suspects: risk discovery, pattern recognition methods to better classify, better segment, better predict areas of our business processes, some of which include ID theft, maybe you've heard of that, refund fraud, financial crimes, but also customer service areas as well. In natural language processing, we're more at I would say, the foothills of this mountain, starting our climb, and we're seeing just an endless set of opportunities here as well. In the customer service area, I mentioned phone calls, right? So think about mining sentiment, which is important for a lot of companies. The IRS is among those that want to be at the forefront of better using those data to understand taxpayer behavior, understand what's in the minds of taxpayers, what they're feeling during a particular tax season, how they're reacting to changes in tax laws that the IRS has to adapt to more often today at the last minute because of the behavior of Congress than ever before. And so being able to use NLP and other text processing methods to look at phone calls, internal correspondence, memos. We get nearly 10 million documents coming into the IRS every year. We're releasing hundreds, almost a couple of 100 million in letters and notices as well. We've got case management systems where case files are being generated. Just huge opportunities for recommendation engines that May was alluding to for human-machine assist, facilitated assist in the space using NLP. I'll also mention speech translation. We have, as a tax administration, treaty partners, a lot of them, that we exchange information with, data. And a lot of that is not in English. And we need better methods, more efficient methods to do language translation. And so we're looking at that. Q&A pairs, in terms of human-machine facilitated assist with chatbots were mentioned during a question, intelligent voice agents, natural language interfaces are all part of this area of NLP that we can put to use in the IRS to improve operations and service delivery again. Just real quickly, in knowledge representation, this is an area that May traversed quickly, talking about graph methods, and there are opportunities here as well. We have a lot of entities, relationships between entities in the IRS, whether they're preparer, taxpayer, business, government, that are inherently conducive to representation through graph methods and graph databases. Whether it's better description of U.S. multinationals, flow-through income, offshoring through aggressive tax planning. These are all areas that are conducive to graph methods.
So Jeff, tell me about the second part of the question that I was asking, because I want to make sure we get to that.
Absolutely. Second part is where are the greatest potential payoffs? Where is the greatest potential value today? And this is, sort